In this video, I'll be solving several problems on rotational dynamics. So for the first problem, we have find the torque from the 12 Newton force about the point O for the following scenarios. So for part A, we have a force being applied 3 meters away, and it looks like it is perpendicular to the rod. So our formula for torque is tau equals R times F times sine of phi, where phi is the angle between R and F. So I always recommend drawing your vector R, which points from the axis of rotation, so our little green point on the left, our pivot point, to where the force is being applied, and then go back to that point and draw your force vector, which is going straight down. So this means the angle between the two is just 90 degrees. So that's going to make our calculation easy since sine of 90 is just 1. So this becomes 3 meters times 12 newtons, and that is 36 Newton meters. For part B, we have our same force, but it's at a slightly different angle. So we need to do this the same way. So RF sine of phi. Our vector R will point in the same direction. It's a little bit shorter since it's only 2 meters, but it points in the same direction. And then our force F is down and to the left. So this angle, if we continue our force vector upward, so up and to the right, just extend it, then the angle that we were given was this angle here between the force and the horizontal. So if we want to get the angle phi, which is between R and F, then we need to subtract 50 from 180. So that will give us 130 degrees. And now we can just plug in. So this is 2 meters times 12 newtons times sine of 130, and that gives 18.4 Newton meters. And for part C, we can do the same thing, except we notice that F is radial. It's along our vector R. So just to show, if I draw my vector R, it's still from the pivot point to the right where the force is being applied. If I go back to that point and draw my force F, then these are 180 degrees apart. And since sine of 180 degrees is 0, this means that our torque is going to be 0. We have another rod that has 3 forces acting at one time, and we're asked to find the net torque about the point O for the forces acting on the rod. So this means we need to sum up all of the torques. So we're going to have R1, so the distance from the first force to the point O, times F1 times sine of the angle between F1 and R1, so we'll call that phi 1. But we can already see that this is going to be 90 degrees, so sine of 90 is just 1, so that kind of just goes away. And then we're going to have the torque from our second force, so R2, F2, sine of the angle between those. And then the last one, R3, F3, and sine of the angle between those. Okay, so first we may want to get some directions for all of these. So if I draw my rod again, draw my pivot point, this first force is going to cause a clockwise rotation about the point O. So F1 is going to be a negative torque, so this will be negative. The second force is up and to the right. It will also cause a clockwise rotation, so it will also be negative. So we're going to have a negative for our second torque. And then the last force, if you were to pull on it to the left, that's going to cause a counterclockwise rotation, so it will be a positive torque. Okay, so that gives us our direction. So now we just need to plug in. So R1 is going to be the full length of the rod, so 2, 2, and 1, so that's a total of 5 meters. And F1 is 30 newtons. Okay, and F2 is negative. Give myself more room. R2 is going to be applied 2 plus 1 meters away, so 3 meters, and it is a 20 Newton force. But we need to find the angle phi 2. So if we do that, I'm going to draw my vector R, which points from the point O to where the force is applied, so straight up. And I'm going to go back, so this is R2, and draw my force. So this is F2. And the angle that we're given, if we just kind of extend our two vectors back out, the angle that we were given was this angle, 60 degrees, but now these are just vertical angles. So it turns out we were given the angle phi, because it's just the same thing, it's just 60 degrees. And so this will be sine of 60. And then for our third torque, we have F3 is just 1 meter away from the point O, and F3 should be 15 newtons. And it, again, is also 90 degrees. So if we add all these together, we get minus 150, and then minus 60 times sine 60 plus 15. So this gives you 100, or minus 187 Newton meters. Or you could write this as 187 Newton meters clockwise. Put a little arrow showing that your direction is clockwise, and then you can make it positive. For the next problem, we have a rope that is wrapped around a horizontal solid disc with a diameter of 0.5 meters. The disc has a moment of inertia of 7.5 kilogram meters squared about a vertical axis through its center. If the rope is pulled by a constant force of 53 newtons, find the angular acceleration of the disc. So I'm going to start off by drawing my little disc, and then I have my force that's going to be pulling, my constant force of 53 newtons. It gave me a diameter of 0.5 meters. Okay, so the first thing I can do is I can use this force and figure out what torque it's going to apply to this disc that's going to rotate about its center. So if I do that, the torque is equal to RF sine of phi, the angle between them. And we can see that this is a force that's applied tangent to this circle, so the angle is just going to be 90 degrees. So this will be the radius, or the distance between the axis of rotation to the force, which is equivalent to the radius. So 0.25 meters times our force, 53 newtons. And that will give us a 13.25 Newton meter torque. Okay, so my vector R was up, my force was to the right, and so phi was just equal to 90. So I could kind of ignore that. Okay, so now in order to find the angular acceleration, I need to use Newton's second law for rotation. So this says the sum of the torques is equal to the moment of inertia times the angular acceleration. And since this is the only force applying a torque, then the sum of the torques is just the torque we've already found. So the acceleration is going to be this torque divided by the moment of inertia. And we're given the moment of inertia of the disk, so we can just plug in. So this is 13.25 Newton meters over 7.5 kilogram meters squared, and this is going to equal 1.77 radians per second squared. For the next problem, we have a horizontal disc that spins, making 4 complete revolutions in 1 second, and has a moment of inertia of 1200 kilogram meters squared. A block weighing 200 newtons that was sitting at the center of the disc is pulled 1.5 meters from the center. Find the angular speed of the turntable when the block is at this position. Okay, so if I draw my turntable or my disc before and after, initially this turntable or disc is spinning with some initial angular velocity, and it has some moment of inertia. And then apparently there's a box at the center, but since it's at the center, it's r equals 0. It has no moment of inertia about an axis running through the center. But then it gets pulled out some distance away, so it's 1.5 meters from the center. And so now that's going to contribute to the moment of inertia of this disk. And so the angular velocity is going to change because it has a new moment of inertia. So for this, we can use conservation of angular momentum. So typically, if you find that your mass is getting redistributed or your moment of inertia changes, that's kind of a sign for you to maybe try using conservation of angular momentum. So this means the final moment of inertia times the final angular velocity will be equal to the initial moment of inertia times the initial angular velocity. Okay, so at the end, the final moment of inertia will be the moment of inertia of the disk plus the moment of inertia of this block times omega f. And initially, the moment of inertia is just the moment of inertia of the disk times its angular velocity. So we know what the moment of inertia of the turntable is. It was given to us, 1,200 kilogram meters squared. And then the moment of inertia of the box, well, it's just an object, kind of like a particle that's some distance away. So it's just going to be mr squared. So I have this, not the disk, the block, will just be the mass of the block times its distance away squared. And so we need its mass, and we were given its weight. So the mass of the block will just be its weight divided by g. And then we were given the initial angular velocity, but we were given it in revolutions per second. So omega I was 4 revolutions per 1 second. So that's going to be, needs to be converted to 2 pi. So multiply by 2 pi radians per 1 revolution. And that will be, just leave the pi, so 8 pi radians per second. And now we're about ready to plug in. So if we solve this for omega f, just by dividing the right side by the total moment of inertia at the end, then we get this, and we're ready to plug in. So this will be the moment of inertia of the disk, which was given 1,200 kilogram meters squared, times the initial angular velocity we just got, 8 pi radians per second, divided by the moment of inertia of the disk again, so 1,200 kilogram meters squared, then plus the mass, which we said is just the weight over gravity, so this will be 200 newtons over 9.8 meters per second squared. If you want to go ahead and do that separately, you can do that. It might be a little bit easier. Times 1.5 meters squared, its distance away from the center. If you plug all of that in, you get 24.2 radians per second. In the next problem, we have a 10-gram bullet that is shot at a 20-kilogram wooden sign that is hinged at the top and hanging down. The sign is 1.5 meters wide and 1 meter tall when it is hanging. If the bullet is initially traveling at 350 meters per second and then is embedded into the wooden sign 0.75 meters from its hinge, find the angular velocity of the bullet and sign after the collision. So at first, we have this bullet that's moving, and it's going to hit a sign that is hinged at the top, and when it hits this sign and the bullet together, the bullet is embedded in the sign, they're going to start to rotate. And so I'm going to draw a view from the front. So this would be a side view. In the front view, show the sign hinged at the top, and then it is 1.5 meters wide and 1 meter tall. Okay, so the bullet's going to kind of go this way. And so we need to find the moment of inertia of this sine. So if I draw sort of a rectangular plate, then with a width A and a length B, and it's rotating about an axis along its side, like the sine is, it's going to rotate like this, then the moment of inertia for a plate about this axis is going to be 1/3 its mass times A squared, where A is the dimension that is perpendicular to the axis of rotation. So now that we have this, we can use conservation of angular momentum, LF equals LI. And so we have the moment of inertia at the end times the angular velocity at the end. And the initial angular momentum is just going to be the angular momentum of the bullet initially, since the sine isn't moving. And so we need to figure out what IF is. Well, IF is just the moment of inertia of the sine plus the moment of inertia of the bullet. So the angular momentum of the bullet, it initially doesn't have angular momentum, but just before it hits the sine and starts to rotate, it gains some angular momentum. So the angular momentum of a particle is mvl, and the moment of inertia of the bullet, we also need that. Again, since it's a particle, just be mr squared, or since we use L for the length, we could write this ml squared. In both cases, L and R just the distance from the object or the particle to the axis of rotation. So now if we just start plugging in, we get the moment of inertia of the sine, which we said is 1/3 its mass, it's 20 kilograms, times A squared. So A is the distance from the axis, from the side that's perpendicular to the axis of rotation. So in this case, that is 1 meter. So that's squared plus the moment of inertia of the bullet. So that's going to be ml squared. So this is a 10-gram bullet. So that will be 0.01 kilograms times L squared. Well, it is 0.75 meters when it hits from the axis. That squared times omega F. And this is going to equal the angular momentum of the bullet initially, so mvl. So this is 0.01 kilograms times 350 meters per second times 0.75 meters. And if I go ahead and solve for these numbers, I get 6.67, this is kilograms, meter squared times omega F. And the number on the right is 2.625. And that'll be kilogram meter squared per second. And then if I divide both sides by 6.67 kilogram meter squared, the kilograms and meter squared will cancel, and I get 0.39 radians per second. For the next problem, we have a single bicycle wheel with a mass of 2 kilograms that is lying in a horizontal plane and rotating about an axis through its center at 700 radians a second. The bicycle wheel has a radius of 30 centimeters, and if the wheel takes 45 seconds to come to a stop, find the torque exerted by friction in stopping the wheel. Okay, so friction is a force that's applying a torque that's going to slow down the wheel as it rotates. And so we can use Newton's second law. So the sum of the torques, so in this case, the only torque will be the torque from friction, will be equal to the moment of inertia of the wheel times its angular acceleration. So in this case, that's the torque from friction. Okay, so the moment of inertia of the wheel, that will be, it's a hollow wheel. Okay, so a bicycle wheel just has spokes in the center, and we can ignore those. And most of the mass is along the outside, so it's just a hoop or a hollow disc. And the moment of inertia of that would be mr squared. So that's going to be 2 kilograms, the mass of the wheel, times its radius, or 0.3 meters squared. And that gives 0.18 kilogram meters squared. And so now in order to find the torque exerted by friction, we have the moment of inertia, we just need to find the angular acceleration. So we're going to assume its angular acceleration is constant, so we can use our kinematic equations. So we can use omega equals omega naught plus alpha times time. We know when it stops, the angular velocity is going to be 0. Let me do that in a different color. And we know what our initial angular velocity is. So if we solve this for alpha, we just get minus omega naught divided by t. So this will give minus omega naught, which is 700 radians per second, over the time, 45 seconds. And this will be 15.56 radians per second squared. And so now if we plug into the torque from friction, then this will give us moment of inertia 0.18 kilogram meters squared times alpha, which was negative. This negative sign just tells you that it's slowing down in this case. So minus 15.56 radians per second squared. And that will give us 2.8 Newton meters. So it didn't tell us which direction it was moving, so our positive and negative sign won't indicate clockwise or counterclockwise. It just means that it's in the opposite direction that it was initially rotating. So maybe I'll put a note of that. But if we knew it was going clockwise or counterclockwise, then we could put in the direction. In this case, it's just opposite direction that it was initially rotating. In the next problem, we have a hoop with a diameter of 12 centimeters that is rolling without slipping with a linear velocity of 3.4 meters per second. Find how long it will take the hoop to come to a stop if it begins rolling up a hill with a slope of 15 degrees. Okay, so initially it is both translating and rotating, so it has kinetic energy. And then when it goes up some height, so it changes its potential energy, it's going to stop. So that means that kinetic energy is going to turn into potential energy. And so this is a candidate for using conservation of energy. So E final equals E initial. So at the end, the mass of this hoop is just going to have potential energy, so mgh, no kinetic energy. And initially it is rolling without slipping, so that means it has both translational kinetic energy, 1/2 mv squared, and rotational kinetic energy, 1/2 I omega squared. Okay, and then it has no potential energy at the end. We will call where it starts y equals 0. And so since it is a hoop, it will have a moment of inertia of mr squared. So if I plug that in, and this happens a lot in conservation of energy problems where you have rotational kinetic energy, you end up substituting in for the moment of inertia. So this will be mr squared. And then for omega squared, we can use the fact that V equals R omega. So omega equals V over R. If we plug that in, we get V squared over R squared since omega was squared. Okay, and now we can simplify a bit. So I'm going to get rid of this. First thing we notice is there's a mass in every term, so that goes away. And then on the right, we have an R squared over an R squared, so that goes to 1. And we get GH equals 1/2 mv squared plus 1/2 mv squared. So we have 1/2 and 1/2, so that just equals v squared. And all of these were our initial velocities since they were on that side. Okay, and so now we can solve this and find that the height that the ball is going to roll before it stops is equal to vi squared over g. Okay, so now we can do a little bit of geometry, trigonometry. So our slope is 15 degrees, so this forms a right triangle with the ground. And the distance that it goes is going to be the hypotenuse, we'll call it d. and the height, h, is what we just found. So we can get a relationship between the two. So h, the opposite side, will be the hypotenuse times sine of 15 degrees. And now we can use the fact that our average velocity is just equal to the distance that it travels over time. And the average velocity is also, we can just do a mathematical average. So it started at some initial velocity and it ended at some final velocity. So we can just add those together and divide by 2 and get another definition for average velocity. And here VF is going to be 0 since it's going to stop at the top. So since these are both average velocity, we can just set them equal to each other. And that's going to give us that D is equal to VI times T divided by 2. Okay, so we got D over T equals VI over 2, and we just multiplied by T. Okay, and so now we can plug all of this in here, and we get H is VI times T over 2, all times sine of 15 degrees. And then we have two expressions for H, so we can set those equal to each other. So if we do that, we have VI times T over 2, sine of 15 degrees is equal to VI squared over G. So one of our VI's is going to cancel, and we can solve for time. So here time, we're going to divide by sine of 15 and multiply by 2. So this will be 2 times VI divided by G, sine of 15 degrees, or 2 times our initial speed, 3.4 meters per second, divided by 9.8 meters per second squared times sine of 15 degrees. And that's going to equal 2.68 seconds. Okay, so there's quite a bit of steps here, so you may have to go back and see what we did, but we're looking for a way to introduce time. And so once we solved for conservation of energy, we had to use some other relationships to bring out time, and then we just set things equal to each other and solve for what we're looking for. The next problem, we're going to find the angular momentum of the moon orbiting the Earth. So we have the Earth, it's a square, not a circle, and then we're going to have the moon, and again, circle, and it's going to be orbiting the Earth. So this is the mass of the moon, and it is some distance away from the Earth. Call this R of the moon. And the angular momentum of the moon is just going to be L equals R. It's distance away from the point about which it's rotating, so the center of the Earth, times its momentum, or R times its mass times its velocity. And then we can also use this relationship, V equals R omega, and then we can plug this in here. So we can rewrite our angular momentum as, well, we have one R, and then times mass, and then our velocity is just R omega. So now we have two R's, so this is going to be M R squared times omega. And then we could look up the mass of the moon. It's 7.35 times 10 to the 22 kilograms. The distance from the moon to the Earth is roughly 3.84 times 10 to the 8th meters. And the angular velocity of the moon, well, it makes one revolution every 27.3 days. Okay, so you may know that it does it roughly every 27, 28 days, or you could look this up, and we want to get this in radians per second. So that is one revolution is 2 pi radians, and then 1 day is 24 hours. 1 hour is 3,600 seconds, or the moon rotates at 2.66 times 10 to the minus 6 radians per second. Okay, so now we can just plug in. So we have the angular momentum is M, so 7.35 times 10 to the 22 kilograms, times R squared, its distance about from the axis of rotation or the center of Earth, 3.84 times 10 to the 8th meters, all squared, times its angular velocity in radians per second, 2.66 times 10 to the minus 6 radians per second. And that gives an angular momentum of 2.88 times 10 to the 34 kilogram meters squared per second. In our last problem, we have a long wooden plank that's suspended from 2 cables and used as a small bridge. The plank is 2 meters long and weighs 220 newtons. There is a 20 kilogram box placed at the left end of the bridge. The cable to the left makes an angle of 40 degrees with the horizontal, and the cable to the right makes an angle of 65 degrees. Find the tension in the 2 cables. In this case, we want to first draw a free body diagram, make sure we know all of our forces, especially since we're looking for 2 forces. So we have 2 unknown forces. This tension is going to be pulling on the bridge. Call this T2, and it's at 65 degrees. Then we have our other tension, T1, pulling up and to the left at 45 degrees. The weight of this entire bridge will treat at the center of mass, so right in the center. So this is the weight of, called the plank. And then the box to the left is also exerting a weight. It's at the very edge, so this will be the weight of the box. And so the first thing you should think to do is to sum up all the forces. But notice if you sum up all the forces in the x or the y direction, both T1 and T2 have x and y components. And so we would always have 2 unknowns, so we couldn't solve them right away. So the easiest thing to do is to sum up the torques, because this plank is in rotational equilibrium, so it's not rotating or translating. So I'm going to take the sum of the torques about the left end, so about this point, okay? Because what that's going to do is it's going to get rid of T1 and the weight of the box. Since their location is at this point, they're not going to cause a torque about this point. Their R, or distance from the axis of rotation, will be 0. So the forces that will cause torques will be T2 and the weight of the plank. So the T2, the force T2, will cause a counterclockwise rotation, so that's going to be positive. So it's going to be the force times the distance. So the T2 is our force, times our distance r away, which is 2 meters, times the angle, sine of the angle between them. Okay, so this is going to be, if I draw my vector r, pointing from the axis of rotation to where T2 is being applied, it's going to be to the right. So this is R2, and then T2 is this direction. So that means phi will just be this angle, which is what we're given, so it's just 65 degrees. So this will be sine of 65 degrees. And then minus the weight of the plank is going to cause a clockwise rotation about this point. Okay, so that will be negative. So minus the force, which is going to be the weight of the plank. So I'm just going to go ahead and plug that in. That's going to be 220 newtons times its distance away. Well, since it's in the center of this 2 meter plank, it's going to be 1 meter away. And it is at a 90 degree angle. So R is to the right and it is down. So phi is just 90. So if you plug that in, first of all, set this all equal to 0 since the sum of the torques is 0. If we solve for T2, so we move 220 to the other side, 220 Newton meters, and then divide by our 2 meters times sine of 65. When we plug that in, we get 122.4 newtons for T2. Okay, so now we can do something similar for the right side. So if we sum up the torques about the right point, so now we're going to sum up the torques about this point. Okay, that's going to get rid of T2, even though we already know it. It's going to get rid of it, so we don't have to worry about it. So we sum up the torques about the right. So if we sum up the torques about the right, then T1 is going to cause a counterclockwise rotation. So it's kind of pulling up a little bit. So it's going to cause a rotation this way about the point on the right. So that is clockwise, so that is minus T1. It is 2 meters away. It's the full length of the plank away. And then times sine of the angle between them. So if we were to do that, then we have R1 points from our point on the right, and then T1, and to do that in another color. So T1 is up and to the left, and so the angle that it gave us, 45 degrees, that is our phi. So this is sine of 45. And then the weight of the box is also going to cause a torque, so it's going to cause a rotation this way about the point on the right. So we will get a counterclockwise rotation or positive torque. So this is going to be the weight of the box, which is just 20 kilograms times g, 9.8 meters per second squared, times the distance away. So it again is 2 meters away. And then it's 90 degrees again, since it's straight down, so it's just sine of 90. And then we get yet another torque from the plank. So that is again 220 newtons. It will be counterclockwise. So it's going to cause a rotation like this. So that will be 220 newtons times its distance away. So again, it's halfway in the middle of the plank, so 1 meter, and it makes a 90-degree angle. So sine of 90 is just 1. Okay, so now we need to solve for T1. So we'll need to move it to the other side and then divide all of this. So 20 kilograms times 9.8 meters per second squared times 2 meters plus 220 Newton meters. So this term and this term. And then we moved T1 and all that term to the other side to make it positive, and now we need to divide by everything in front. So 2 meters times sine of 45 degrees, and that will give us a tension of 338 newtons. Okay, so you have to go through for each of these. Make sure you know first the angle phi, know the distance away from the axis of rotation, and you're free to choose which axis you want. So make sure you draw a little point and get your distances right. Okay, so each of these have their own distance away. And then get your angles right. Two, I wanted you to notice for the mass of the box, we were only given the mass in kilograms, so we needed to multiply by g in order to get the force. And then we had a distance, and we could have potentially had an angle as well. And so this could have been a long term. And then when we had the weight of the plank, it was just the weight times the distance. So make sure you pay attention to whether or not you're given a mass or a weight. And be sure you don't leave out that factor of g. So I hope these problems helped you get through and understand more of rotational dynamics and calculating things like torques, using conservation of angular momentum, Newton's second law for rotation, all of that good stuff. And I'll see you in the next video.